Okay, so again, it's on velocity and acceleration for section 13.4. Just let's go ahead and make sure we've got all the definitions. So R of t is a position function. It inputs a time and outputs a position vector. Okay, now all of these are functions of time, but there's three component functions. So for instance, the R of t will have an x of t, a y of t, and a z of t. And there's no z component if it's two-dimensional. Okay, here's a question. Would you guys respond if you can see all of that? Can't tell? We can, yes, 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 yes. Fantastic. Okay, great. So we've got our position function and then velocity. R prime of t is velocity. Okay, which is, as you know, we'll just call it v of t. These are all vectors. Okay. And then r double prime of t is acceleration. Which we denote, of course, that's v prime of t, but it's also a of t. Okay. Now, when we want to find projectile motion where we shoot something into the air and there's no friction, we have to solve the differential equations, and this is going to be a vector equation. So yeah, I know most of you guys have seen this before, but we're going to do it with vectors just so you can see how that works. So this is projectile motion. A vector differential equation. Okay, so the assumption, well, there's a couple of assumptions. Okay, the first one is just nonsense, and it is that there's no friction, so no air resistance. And the only reason why is because if you put air resistance in, the problem becomes much more advanced. Not that it can't be done. And then secondly, the acceleration due to gravity is constant. Okay, so the second assumption here is just a simple statement that a of t, which is acceleration, this would be constant. And because it's acceleration due to gravity, we'll just call it g. Oops, that's a p. So g is a constant vector. And why not give g components? We're going to do this two-dimensionally under the assumption that there's no wind or any sort of wind resistance, that this thing is not going to get blown left or right. It's just going to go up and then come down again. So there is going to be no horizontal component to gravity, only vertical. And I'm just going to do a negative and a little g. Okay, so that's right there, approximately 9.8 meters per second squared, or 32 feet per second squared, either way. Any questions? All right, so then from that assumption, we have our differential equation. Acceleration is g. That means r double prime of t is g. Okay, that's the differential equation. Differential equations in physics usually have what we call initial conditions. So the initial conditions, oops, you can't know the position function without knowing the initial velocity and the initial position. Oh, I'm going to add some people to the class here. There we go. Okay, so the initial conditions are, first of all, we need an initial position. R at time 0 would be r sub 0. And if you want, you can give that coordinates x naught, y naught. Okay, so that's initial position. And then secondly, v at 0, that's the initial velocity, is going to be v sub 0. Okay. And before we get too deep in, let's look at this trajectory. So maybe up here, I'm just going to draw a horizontal line. And I don't need this initial position to be down at ground level, but I'm going to do this anyway. So I'm going to shoot this trajectory up. It presumably follows a parabolic path, and then it's going to hit somewhere. Okay, so this initial position here is just R0. Like that. And then there's an initial velocity vector, so I'm actually going to put a little vector on this, maybe in red. Just a tangent vector like that. And let's call it V0. Okay. So, any questions about this yet? I'm looking at you guys right now to see if anybody's got a hand up. And nobody does. And I'm looking in the chat. I don't see anything. So I assume you guys are all muted, but you're doing fine. So don't feel shy about saying something if you've got something to say. Okay, so that's my initial velocity vector there. Maybe let's blow up the initial velocity just to make it a bit larger here, and we can think about its components. I think I'll switch colors here. Okay, so the initial velocity vector will have an angle of inclination, which we'll just call theta there. So the horizontal component will be, let's say the magnitude of V naught. So but the magnitude of V naught, we'll routinely just use a script V naught times cos theta for the horizontal component, and script V naught times sine theta for the vertical component, and just denote that script V naught is just speed, which is the magnitude of velocity. Like that. Okay, and I'm looking up to see if anybody has questions. I see some people need to be admitted. There's Alicia. Hi, Alicia. I know you had trouble getting in. Sorry about that. Okay, I'm going to pause for just 1 second, guys. I had to tell my kids to shush a little bit. Yeah, sorry about that. Okay, everybody's in. Any questions? Y'all good? Looks like it. Okay, you guys still seeing all this?
Yes.
Okay, oh, awesome. I heard a voice. Okay, so then I'm going to keep going here. So we've got speed. And so the initial velocity vector here is v naught, which is going to be, as we said, script v naught cos theta, comma, I need more space, and script v naught sine theta. Okay, so that's our initial velocity. Okay, so that's just the posing of the differential equation. Now, what we want to do next is to solve the differential equation. This is easy, but we're just going to do it by antiderivatives. But it's a vector differential equation. Okay, so when you take an antiderivative and add a constant, it has to be a constant vector. Okay, so here we go. The differential equation is just r double prime equals g. And so taking an antiderivative, r prime will be g t plus c. Okay, let's say c1, because we're going to have to do another antiderivative. And just real quickly from there, we can say that r prime at 0 is g times 0 plus c. Okay, now of course, r prime of 0 is the same thing as velocity at time 0. So velocity at time 0 turns out to just be c1. But up above, we say that velocity at time 0 is initial velocity of course. So let's just say this is equal to v0, like that. And then we can step back and say, all right, so r prime is g t plus v naught. And therefore, r double prime, r itself will be, now taking an antiderivative, 1/2 g t squared plus v naught t plus another constant of integration, c2, let's say. And recognizing that r of 0 will come up here. And r of 0 would be 1/2 g times 0 squared plus v naught times 0 plus c2, but that's got to be initial position. So this whole thing is equal to c2, which is r0. Okay, so c2 is r0. That means r of t is 1/2 g the vector g, t squared, plus initial velocity v naught t, plus the constant of integration that turned out to be r naught. Okay? So then we can rewrite our equation r, maybe I'll just say r of t now to make it official, is 1/2 g t squared plus v naught t plus c2, which we decided was initial position r0, like that. Okay, and then so that's the solution. Usually we like to put this into an explicit form involving the x and y coordinates, but you don't have to. This would work just fine. Maybe as a reminder, g was 0, negative g without a vector symbol over it. So that little g, remember, is the 9.8 meters per second squared, or 32 feet per second squared. And then v naught was initial speed, initial velocity, which is initial speed times the cos theta. That's the angle of inclination. And script v naught, again, speed times sine theta. Okay. And then, of course, r naught is the easy one. The initial position, you just have an x naught. And so let's go ahead and pull all this together. So RT is 1/2. I'll put in a g, which is 0, negative g, and that's times t squared, plus v naught. Well, that's going to be script v naught cos theta, script v naught sine theta. That's all times t, and then plus r naught, which is just x naught, y naught. Like that. And so you can see this is going to come together and form the x component and the y component of the trajectory as the object flies through the air. Okay, I don't see any new faces yet. Looks like everybody's doing okay. No chat comments. All right. Now we're going to combine these into one vector. So I'm going to do this in one shot here. R of t is going to be, in the first component, I have 1/2 times 0 times t squared, so that doesn't amount to anything. Then you have the v naught cos theta times t, so let's put that in here. Script v naught cos theta times t, plus the x component of the initial position is x naught, so plus x naught. And then for the y component, you have a 1/2 times negative g times t squared. So we'll write that as negative 1/2 g t squared, plus the y component of the next vector is v naught sine theta, and that'll be times t, script v naught sine theta, t, and then plus y naught. Okay, now the first component, you can think of this as parametric equations now, that x would be the first component, and y would this be the second component. And so the parametric solution of the vector differential equation would be like this. X equals script v naught cos theta t plus script x naught, and then y would be script v naught, oops, my bad, negative 1/2 g t squared plus script v naught sine theta t plus y naught. Okay, and then I'd make a note here, in almost all the problems in the homework, x naught and y naught are both 0. So, so if r naught is the origin, that means x naught, y naught is 0, 0. Okay, and most problems assume this in the homework. Okay, any questions about that? I'm looking to see, again, I'll remind you one more time, you guys are muted, but you can unmute yourself anytime and interrupt me if you have a question. Also, on the participants tool, if you click on Manage Participants, I believe near the bottom of that, there's a thing where you can raise your hand. I don't have that, and I assume that's because I'm the host. Okay, so nobody has, I don't think anybody has their hand raised, and nobody's interrupting me in a good way or a bad way. So I'm going to keep going here. Okay, so we got our parametric solution. So I'll just make a note here that x naught is usually 0. And same thing for y naught. Okay. So we are going to do a quick little example here. So suppose a projectile, is fired at 450 meters per second. And the question is, give two angles that allow the projectile to hit a target 2,500 meters away. Oops. Okay, so that sounds tricky. Oops. Now, when they tell you how far the projectile is going, that's called the range. So let me go ahead and just draw a little picture of this. And we don't know the angle of inclination here. But that's really what they're asking for, right? Okay, now the target, it's not stated, but the target is on the ground. Okay, your initial position is also on the ground. And so that's the origin. Okay. And we know the initial speed, and we know where the target, how far the target is. So let's put that on here as well. So this is going to be 2,500 right there. And I'll go ahead and put 0 for the origin over here. Okay. And so we're worried about the angle of inclination. I'll go ahead and put an initial velocity vector here. So that's V0 here. Like that. And the angle we're interested in here is this theta. Oh, I'm sorry, there's 2 people waiting. Okay, sorry about the slow response for you. Those of you guys are waiting. I don't know why I have to admit you into the room. I hope there's a way so that they come in automatically next time. So I apologize for the slow admit. Anyway, let's keep going. We're looking for that angle of inclination. Let's go ahead and work out a formula for the range. Anybody have any comments or questions? And again, I will be posting this video. And even at the break, if you want, I can send you a PDF. If you've come in late, I can send you a PDF at the break of what you've missed. Okay. But let's go ahead. And in any case, I'll send a PDF to the whole class of the notes. And I'll post them on Canvas. Okay, so I want to talk about the range for a second here. So the distance from the origin to where the target is, that distance is the range. Okay. So we're going to figure this out real quick. First of all, when x equals the range, we want the y-coordinate to be 0 because the projectiles hit the ground again. So let's go ahead and say we want y to be 0. Any questions? All right, and then I'm going to go ahead and copy the y part of the parameterization. Remember, y0 is 0 here. So I just need the first 2 terms in the formula. Okay, so this. And then we'll set it equal to 0. Okay, and then of course we're just going to solve that for t. So factoring out the t, you get -1/2 gt plus v naught, script v naught, that's the speed, sine theta equals 0. And yes, the object is on the ground at 2 different times. The first time when the object is ground is when it's fired. So initially when time is 0, the y-coordinate is also 0. We knew that and we don't care about that. This is the one we want to be 0 right now. So we're going to do -1/2 gt plus script v naught sine theta. That has to be 0. And remember, we're solving for the speed. Actually, we'll get that. The speed is unknown though right now, and we will solve for it. But for the moment, I think we're going to have to solve for the time. So let's go ahead and get that real quick. So at this time, when the object hits the ground, I think t is going to be, if you move the v naught sine theta to the other side, it will be negative script v naught sine theta, and then divide by the -1/2 g here. Like that. I think we're going to get 2 script v naught sine theta over g. Okay, so I'm going to just pause here, see what's going on. Someone is trying to get in. So that person's admitted. And I don't see any hands up. Any of you feel free to unmute yourself and interrupt me. And also in the chat, I don't see any questions. On the toolbar, if you see a chat tool, you can click on that to ask questions. There's a more button also that might have your chat command in there. But then also, if you click on participants, you can raise your hand in there. I heard someone unmuted. Was there a question? Anybody? Yeah, Alicia, can you unmute yourself?
Yeah, I went ahead. I have a question here. So you did t equals 0 here for the y, but now we're working this out. What are you doing with this t over here, the one that's outside of the parentheses? What's going on with that?
So keep in mind that there are two moments when the object is on the ground. Initially, the object is on the ground as it's being fired. And then later, it goes up in the air and later hits the ground again. And that's another time. So it makes sense that there's two solutions to the equation. Okay, we're trying to find out when this thing hits the ground. So one time comes from this factor. You know, it's a quadratic equation, right? So with a quadratic, we expect those two solutions. So on one, t is 0. We already knew the object was on the ground at time 0. So I'm disregarding that because it's not the useful one.
Right.
I'm trying to find when it hits the ground after flying through the air. So that's when the other factor of this factored equation. Does that make sense?
Kind of.
Well, I mean, you realize there's two moments when this thing's on the ground, right?
Yeah, when it's at the origin and then when it hits the target.
Right, and so when you solve for the time, you know, I set y to 0 because I want the y coordinate to be 0 here.
So you're just solving for what's in the parentheses for the second.
Right, you know, when you have the zero product, something times something equals 0, then you set both of them to 0, right?
Okay, I got you.
One of those has to be 0 for the product to be 0.
Right.
So I'm solving them individually, and I get those two moments when the object is on the ground. So it's a quadratic equation. It gives two solutions because this thing we're looking at happens twice.
Right. Okay, I got it. Thank you.
Perfect. No worries. Okay, so now I have the time when the object hits the ground, but I don't actually have the distance when the object hits the ground. So the distance is an x-coordinate. That's a horizontal length. So the range is going to be x at the time above. Meaning the one we just talked about. Okay, so all we have to do is just evaluate x up here. So the x coordinate way up here in the parametric solution to our vector equation, we're ignoring the x naught because we're assuming the initial position is at the origin. So I'm just copying the x component here. Okay. And so that's the distance, but I need the range, and the range will be the distance at the time that we solved for above. So this will be super easy. We just say that this is equal to script v naught cos theta, and then the t becomes 2 script v naught sine theta over g. Okay, any of you wants to interrupt, feel free to unmute yourself and jump in. Okay, then the rest is just a bit of algebraic simplification. Okay, so I'm going to write this as, we're going to do a script v naught squared because there's two of them. And then you'll see the 2 sine theta cos theta. okay, which should remind you of a trig identity. Anybody want to unmute real quick and say what that thing is? Apparently not. That's cool. I forgive you. So it's V naught, script V naught, that's the speed, squared. 2 sine theta cos theta, as you all know, is sine 2 theta. And this is over G. Now that'll make the rest of the problem a lot easier. Remember, we're trying to solve for theta when the range is, I believe, 2,500 feet. Okay, so let's just kind of make this important here. Okay, you will use this multiple times in your homework. And so whenever the range of a projectile comes up, that's the formula you need there. Okay, any questions? All right, so, and then if we back up a little bit, remember, I'm gonna slide back up here for a second. Just remember, we need the range to be 2,500 feet. And the question, let me slide up here. Where'd it go? Right here. So we're trying to find two angles that allow the projectile to go 2,500 feet. So it's kind of nice that there's a 2 theta in this equation because that's going to give us two angles. The easy way, two angles that are sort of not the same or coterminal or anything like that, or negative angles or any of that. Okay, so I'm going to take this range formula here. I'm going to bring it on up here and just set it to 2,500. So the range is script V naught square sine 2 theta over G. And we'll set this equal to 2,500. Okay. And so I think I can say sine 2 theta is going to be 2,500 G over script V naught squared. Okay, and probably it's time to get our calculators out. I don't want to finish solving this equation until I have a number for this. Okay, I'm looking to see if anybody's trying to get in. No. And Alicia has, do you still want your, Alicia, do you want your hand up still? You can unmute yourself if you like.
Oh, I didn't know I had to put my hand down.
I know.
Oh, I see. Oh, there we go. Sorry.
It's just like the kid in the back of the room that just won't put the hand down, right?
That's me.
Okay, so going on, let's just go ahead and put the numbers in here. I think this is in meters. Did I say 2,500 meters here? Yeah. And so we're going to do gravity in meters. And way at the beginning of the development, we said gravity in meters is 9.8 meters per second squared. So we'll go ahead and do all that. It's 2,500 times, approximately 9.8 meters per second squared. And then we're going to divide by the speed squared, which I think is 450 up here. Okay, so let's divide by 450 squared. I could almost see, the sign has to be a number between -1 and +1. So if this came out like bigger than 1, then you would know that it would actually be impossible to hit the target. And you can see that it's all dependent on the speed. So if the speed is too small, that makes the fraction bigger. And the fraction would get so big that it would be bigger than 1 in the end. And if it's bigger than 1, there's not a solution. It wasn't fired fast enough. So the object will never hit the target in that condition. But here I think we're okay. I just stole the problem from the book, so that makes me feel pretty good about that. Hey, I should ask if anybody did that computation. And if you did, could you give us a couple of significant, let's not round till we're done. So several significant digits. Uh-oh, I made a mistake. I got a number, when I did it, I got a number bigger than 1, and I know that's not right. So I just had to retype it. Okay, anybody get it? Ooh, Alicia, did you say 0.12098? That's a lot.
Yeah, 0.1209876.
Thank you very much. So we're going to say sine of 2 theta is, I'll just say 0.12, it should be really 10. Just the way that rounds. Okay, so then maybe if I was to remind myself how the unit circle works real quick, it might help me remember, okay, where are these two solutions again? Okay, so the sine is the y-coordinate for an angle, so let me just put a y-axis here. Oops. Something like that. And so I'm going to have that 0.121 right here. And again, as I said, the sine is that y-coordinate, but there's 2 points on the unit circle with that y-coordinate. Okay, so these are the 2 angles. Now don't panic, one of them looks like you're shooting the projectile backward. Follow me on that? But remember, this is 2 theta. So we'll divide this by 2, and hopefully that'll make a little more sense here. So I'm gonna just kind of put a 2 theta there. Both of them are 2 theta. So let's just go ahead and solve for 2 theta by doing a sine inverse on your calculator. So 2 theta, let me hang on here. So that's sine inverse of 0.1210. Okay, and I'm hoping to get more involvement than just one person. Oh, I got a lot of people that did point the other one. So, all right, so don't divide it by 2. Make sure you're calculating. You want to do degree mode? I guess we should do degree mode, you guys. So I'm going to put mine into, I know I'm in radian mode right now. I don't know if I know how to put it in degree mode. I'm using my wife's calculator, super too smart for me. There, I got it. Okay. You know what I need is an on-screen calculator. 1, 2, 1. Okay, that is radians. This may be too much for me, you guys. Anybody have an answer yet? Oh, wait. Thanks. 6.9498. So 2 theta is 6.9498. That's degrees. Or 2 theta would be 180, right? minus that, 6.9498 degrees. Do you guys follow me on that one? Any questions? I'm just looking to see if anybody's putting their hand up. I got nothing. Okay, so if we do 180 minus that, $9,498. So you get anybody get like 173.0 something? My calculator rounded it, which is annoying. So I got 0502. Okay, so both of those are 2 theta. So then just divide them by 2. So this 6.9498 divided by 2. Okay, let's go. I think we should probably do 2 significant figures here because the gravity is only 2 significant figures there. So I don't know, I hate being too uptight about that. Maybe I'll do 3 just to say I did. So the first one you get is 3.47 degrees. Anybody else have the other one? Good. 86.5 degrees. That's 3 significant figures. Thank you. Thanks, Hassan, for that. Okay, so that's almost straight up, right? But both of those, again, this is all assuming there's no wind resistance. A little bit silly. Okay, so basically these are our 2 solutions. Okay, and I think we've answered the question. Now, what time is it? It's almost 7. And I think this is a good time for our first break. But before we go, I want to look and see if anybody's got a hand up. Again, to put your hand up, you click on the Manage Participants link on the little toolbar that they have here. Manage Participants, and then look for your name. No, you don't actually do that. Toward the bottom, you just have a little picture of a hand and you put that up. Or you can type it into the chat, which I don't see. So I'm going to say there are no questions. Okay, last chance for questions. All right. I'm going to stop the recording. Okay, so that's all we're going to do with projectile motion. And now we just want to talk about decomposing acceleration. So I'm just going to put this under the decomposition of acceleration. See, velocity is a tangent vector. It's always tangent to your curve. Okay, that's pretty easy. Okay, acceleration can point in any direction. and acceleration does two things. And so confusing. Okay. It makes you speed up or slow down. Oops. But that same acceleration vector makes you turn. So if you have an acceleration that's pointing straight in the direction you're going, you're going to speed up. If you have an acceleration that is pushing you to the right, you're going to turn. But more often, your acceleration is a combination of both of those. So your acceleration isn't pointing straight ahead or straight to the right or left. It might be pointing kind of at a 45-degree angle ahead, and that's going to cause you to speed up and turn. So what we want to do is we want to break acceleration down into its component parts. Okay, so that's the decomposition that I'm talking about. Okay, so a couple of reminders here. Let's just do kind of a quick review here. First thing we said was we defined a thing called the unit tangent, t. Let's say t of t is a unit tangent. Okay, and this is just the velocity vector divided by speed, or the magnitude of the velocity vector. Okay.
Quick question.
Yeah, go.
Is unit tangent supposed to have a hat instead of a vector?
Yeah, the notation that I'm still really bad at has hats for unit vectors.
Oh, that is a hat. I'm so sorry.
Oh, yeah, it's all good. And thank you for interrupting. It's just so much easier for me because I don't have to keep looking to see if someone's got their hand up. So thank you. Going on, so yeah, that's a unit tangent. Then we had, so let's go ahead and do the differentials. So ds is arc length differential. So this is just speed times time, and speed is the magnitude of velocity. So that's the arc length differential, and of course ds is the magnitude of dr, which is the displacement differential. So this is just r prime without the magnitude of t dt. I'm not going to put the arc length formula up here. It's just the integral of the arc length differential. But just as a reminder then that ds over dt is the magnitude of r prime that follows from ds up above. So this is just speed. And so the unit tangent, if you want to expand that up above, you'd say it's r prime over the magnitude of r prime, which is ds over dt, if you like. That's not necessary, but it will come into play. I think we could do curvature, so kappa is curvature. And the first form, you had a couple of formulas for this. The first one was the magnitude of t prime of t over the magnitude of r prime of t, like that. And we proved another formula at the end of class last time, that it's the magnitude of r prime cross r double prime over the magnitude of r prime to the third. And that's a horrible formula, but sometimes it's actually easier than the first formula. So you just kind of have to look at the situation and think, you know, what's going to be harder to do. I want to go ahead and put in a fact here. The fact was that if the magnitude of r is a constant, then r is perpendicular to r prime for all time. And we talked about how if your position vector's length is constant, that just means you're not moving from the origin, you're not moving any distance away from the origin or toward it. So you're moving on a circle. And the tangent as to motion on a circle is your velocity, and that's got to be perpendicular to the radius, which is your position. So that sort of makes sense. And that fact implies that t prime is perpendicular to t. The unit tangent, the unit tangent, when you take its derivative, it will be perpendicular to the unit tangent. And then the definition of the unit normal, that's n of t with a hat. Okay, so again, this is unit normal. And all you have to do to get something perpendicular to the tangent is to take the derivative of the tangent, because the derivative of the tangent is perpendicular to the tangent. And then, of course, that may not be a unit vector anymore. I'm fixing something over here. So that may not be a unit vector, so I don't put the barb or the hat on it. And you can see this, all these hats and barbs just absolutely bewilder me at this point in my life. Okay, but so this is correct. And just noting the numerator, we know that n is perpendicular to t because t prime is perpendicular to t. And, oh, we need to do that. Did mean to do that. Okay. Okay, so I think it's all good. So real quickly here, I want to make a couple of comments from the definition of the unit tangent above up here. I want to say that r prime, which is velocity, if you carry this denominator over in front, well, I did not mean to do that. Hang on. If you carry that denominator over in front of the unit tangent, you can say that the velocity is ds over dt times the tangent. Okay. So that's just giving the distance and the magnitude and the direction for velocity. The magnitude of velocity is speed, which is ds over dt, and the direction of velocity is t. Okay, so, and then we did a little bit of this last time. So, velocity which is r prime, is equal to ds over dt times t. So acceleration, which is d over dt on v.
Is that ds dt t hat?
Yes. Damn it. There we go. All right, so then acceleration is d over dt times v, or of v, I guess I should say. But I want to rewrite this as d over dt, now applied to ds over dt times t. Okay, and that's going to require a product rule. So you can say this is d2s over dt squared. That's the second derivative of arc length times t. And then plus ds over dt times t prime. Now I'm not doing a hat anymore because there's no reason to think that'll be a unit vector anymore. Now, one thing I want to note is that this is acceleration. And I've just written acceleration into two components. One component of acceleration is pointing in direction of the unit tangent. So this first part is tangential. Okay? And the second part is normal. So that's kind of convenient. Remember, t prime is perpendicular to t. Any questions? So again, the whole point of this was to decompose acceleration into two parts. It's one acceleration, but the two parts have different roles. The normal component is really the part that makes you turn. So if you want to measure that turning acceleration, which we could call centripetal acceleration, we need to look at the normal component of acceleration. And the tangential component of acceleration, we don't actually have a better name for it other than it's the tangential component of acceleration. And that's usually the acceleration people talk about when they talk about how their car is accelerating. They're not thinking about the turn, they're just thinking about the fact that their car is increasing in speed. Okay, so I wanna go ahead and break this down just a little bit more. Because what I want is, I wanna replace this t prime here with a normal component. So if you look back here, maybe let's do a note on the side that n is t prime over the magnitude of t prime, like that. So t prime is n, well, let's say the magnitude of t prime. Times n, like that. So when I refer to a normal component of acceleration, I really do want to use n for that. So I'm going to go back and keep writing on this thing and say, okay, acceleration is d2s over dt squared. And we're gonna change this part at all. This is perfect the way it is, times t. And then plus this other thing, it's a ds over dt times t prime, which I'm going to write the magnitude of t prime times the unit normal. Okay, d2s over dt squared is the second derivative of arc length. So the first derivative of arc length is speed. The second derivative is just called the tangential component of acceleration. It's just increasing your speed. Totally makes sense. There's nothing to do with that formula. The other expression is complicated. So I'd like to clean this thing up. And what I really want to do is somehow to bring curvature into this. So if you remember the formula for curvature, oops, let me use green for this. So for curvature, that's kappa. Okay, and kappa, well, the first formula we had was the magnitude of t prime over the magnitude of r prime. Like that. That's a scalar. And that means the magnitude of t prime is equal to the magnitude of r prime times kappa. And we also know that the magnitude of r prime is ds over dt. That's just speed. So yeah, that's right. So I'm going to circle this. Okay, so I'm going to replace the magnitude of t prime with something that has kappa in it. Okay, so I'm going to rewrite the acceleration one more time. Well, probably another time after that as well. So I've got a ds over dt, d2s over dt squared times a unit tangent, plus I'm going to have a ds over dt times the magnitude of t prime, which is going to be another ds over dt. And then I'm going to have a kappa times m, like that. So maybe ds over d2s over dt squared times t plus ds over dt quantity squared times kappa m. Okay, so this is great. Again, this is a decomposition. Let me clean that up. This is a decomposition of acceleration. The first part is tangential, and the other part is normal. Okay, any questions? I'm going to pause and just see if anybody raises their hand. I'm sorry I've gone a long time without asking for questions. And I'm going to pause for a sec. Looking for hands raised. I don't see that. Just remind you to raise your hand. You can just go.
So, what did you get the plus ds over dt and then t prime?
Do you
Where it says acceleration equal?
right here what I just circled?
No, up.
Okay, this part here.
Yes, that one.
Okay, so I am just doing the product rule. So this right here is a product. And so I'm using the product rule down here. The product rule always gets into two terms. So I took the derivative of the first times the second plus the first times the derivative of the second.
Okay, got it. Okay.
Yep. So all of this decomposition was nothing more than a kind of a well-timed application of the product rule. And the product rule is what splits acceleration into tangential and normal components. It's kind of weird, it's kind of crazy, but it works. Okay, any other questions? Okay, maybe we should draw a picture here before we go too far, because what I really want to do is add one more thing to this. So at some point I'm going to squeeze something in, but I think I should do a picture first. So let's do, I'm I'm gonna start by just drawing a green circle, and then I'm gonna fit a curve to it the best I can. And I want the kind of the curvature of the curve to match the curvature of the circle. You can't see what I'm doing. And I'm sort of exaggerating this, but the idea is that they have matching curvature. Now, I'm going to draw a radius to the circle. Okay. And the radius is rho. The curvature is kappa. Okay. The circle is called the oscillating circle. I think it only has one L. So I know on Monday I kept using two L's. I still haven't checked, but today I'm using one L. And oscillating is not the same as oscillating, which is where something vibrates. Oscillating, actually, if you look it up, it means to kiss. So the oscillating circle is kissing the curve. It's a tangent circle. And so it's kind of weird, but the relationship, oh, and I mean, we can put some of this other stuff in. So I'm going to draw the tangent vector. I'm going to make this kind of small because I want the normal to stand out as well. So I'm going to do a little bit of a small tangent vector here, just like that. So this guy is T. And then equally long will be my unit normal. So I'm doing that there. That guy is N. And then just to make sure it's clear, let's spell out the fact that rho, rho is the radius of the oscillating circle. Okay, and I'm just going to clean this up a little. Okay. And we put down the center of the circle here. And the idea, does anybody remember what the, if you feel brave, anybody feel like they want to say the relationship between rho and kappa? We could just call this an identity. Oops. Relationship between kappa and rho, does anybody remember?
Is kappa 1 over rho?
Exactly right. Kappa is 1 over rho. Thank you. Think about what does the circle become when the radius goes to infinity? Just unmute yourself. What does a circle become when the radius goes to a circle? To infinity, sorry.
A dot or a point?
Now that is a very small circle. But if the radius goes to infinity, just look at one point on the circle and on the edge of the circle and imagine the radius going to infinity. What does this circle look more and more like?
Is it a plane?
Yeah, no, it's just a geometric shape. So think about that, just one spot on the circle. Okay, it's a nice curve, but the radius is going to infinity. Look at that one spot on the circle and think about what the curve looks more and more like. Last chance.
I believe someone in chat said it was a line.
Yeah, it's a line. Thank you, I'm not seeing that. So can you see that as rho goes to infinity, that kappa goes to 0. And so we can see the curvature of a line will be 0. Okay, so we're just talking about that. Now, I want to go back to this thing we were doing up above. Any questions right now? I should open my chat because I don't see it now. Chat. Comes a line, right. Awesome. Looking to see if anybody's got a hand up. Nobody's trying to get in. I think we're good to go. Okay, and then going back to this mess up here, I just wanted to say, let's change the kappa to 1 over rho. And I'm gonna make this a little smaller and squeeze some stuff together for my own purposes. Okay, so acceleration, finally, the last version is it's d2s over dt squared times t plus, I think what I'm going to do is I'm going to write ds over dt quantity squared, and then I would, instead of kappa, what would I put down below it? Thinking about
1 over rho.
Yeah, 1 over rho. So I'm just going to say ds over dt quantity squared over rho, and then that's times the unit normal.
Oh, yeah.
Okay, so when you look at this, and I think what I'll do right now is this is a new page, so I'm gonna say acceleration is this expression, d2s over dt squared times t plus ds over dt quantity squared over rho times m. Okay, so again, this component here is tangential. Okay, and AT is d2s over dt squared. That does not look like a t. Let me fix it. Which is the tangential component of acceleration. Any questions about that? And just remember, ds over, just as a reminder, underneath maybe that ds over dt is the magnitude of r prime, or velocity, if you like. Okay, which is just speed. So the derivative of speed is not acceleration. It's the tangential component of acceleration. Projectile motion. There's someone here called projectile motion. Sort of love it. Yes, projectile motion. Would you like to ask a question? I'm unmuting you. No, I don't know if doesn't look like he wants to unmute. What's wrong? Okay, on projectile motion, what would you like to say? Okay, you're not saying anything. Am I gonna have to lower your hand? Fine, I'm lowering my hand. You know what?
He's in chat. He doesn't have a mic.
He's
and
in
it's
chat.
he says in chat, can you explain the part where it says at? Oh, a sub t probably.
Oh, okay, tangential component of acceleration, AT. Now, the question, what I don't know, okay, so what I don't know is if you're asking me how it came about. I'm just telling you, if you see the acceleration, it has two parts. Okay, one is tangential, the other's normal. And the part that is tangential, we just call it AT. Okay, so that's a special notation. And AT is the rate at which speed increases. And if somebody says, oh, that's just acceleration, I would say no, it's the tangential component of acceleration. Remembering that acceleration has two parts, one that makes you turn and one that increases your speed. So all we've done here is identify the part that makes your speed get larger or smaller. I said increases, but I should say changes, right? Projectile motion. He says, oh, okay, yeah. I was wondering what happened to that. Yeah, gotcha. Just a special notation. Gotcha. So now I know why so many people aren't talking, because you don't have mics. Okay, let's go back to the normal component up here. Okay, so this will be AN. I'm gonna move some things around real quick. Okay, so the normal component is A with a little n subscript. And you can see it's ds over dt squared divided by rho. And if you like, remember that ds over dt is speed and rho is the radius of curvature. So what's a name for this thing? Speed squared divided by radius. Anybody? You can type it or you can shout it out.
Centripetal acceleration?
Thank you. Yes, the normal component. This is assuming you've taken, some of you guys have taken a fair amount of physics, and you know that speed squared divided by radius is centripetal acceleration. That's for circles. And all we're doing here is we're defining that same acceleration, but not in the context of a circle. So this is the normal component of, and then in parentheses, I'm going to say centripetal acceleration. Okay, and of course, AN. No, we're good. I think that's good enough. So I want to just look and see if we've got any more questions. I don't see a question there. Nobody's shouting out. I don't see any hands raised. Okay, gonna wait just one more second in case somebody wants to ask a question. Okay, then I want to go ahead and let's see, there's just a couple of more things to nail down real quickly here. I want to remind you, first of all, formulas for curvature. We had one again that said kappa was the magnitude of r prime cross r double prime over, magnitude, over the magnitude of r prime to the third. Okay. And up above, we had an, and you could put that rho in. So you would say then rho, remember, is 1 over kappa. So rho would be the magnitude of r prime to the third over the magnitude of r prime cross r double prime, like that. And so that guy right there, remember, is the radius of curvature. Okay, and then I wanted to just say AN, the normal component of acceleration, we had as ds over dt squared divided by curvature, which is rho. So I want to go ahead and say that this will be kappa times ds over dt squared. And I'll remind you down here, ds over dt, remember, is speed, so this is the magnitude of r prime. Okay, so I want to say it's kappa times magnitude of r prime squared. Okay, so remember, going this way, kappa is 1 over rho. Okay. And then putting in the formula for kappa, kappa was the magnitude of r prime cross r double prime over the magnitude of r prime to the third. Okay, and then, so that's kappa, and then it's times the magnitude of r prime squared. So this is just the magnitude of r prime cross r double prime over the magnitude of r prime. Okay, so that's an alternate formula for the normal component of acceleration. Okay, so I'll summarize that. So AN, which was, what was the first formula? It was ds over dt squared over rho, can also be written as the magnitude of r prime cross r double prime over the magnitude of r prime. That. We'll do a summary with all these formulas. This is just a pile of formulas. This is what it is. Okay, and then I'm on AT. So just a real quick note on the decomposition. So what if I do this? This expression, if I just took all this from up above, I'm just going to borrow this here, and you can just draw an arrow pointing to this. You don't have to draw this again. Okay, so all I wanted to say, just referring to that, is to say that acceleration is the tangential component times the unit tangent plus the normal component times the unit normal. And I want to show you what happens if you dot both sides with the unit tangent. So we're going to dot both sides with t. Let's say by t. So you get a dot t equals AT times T dot T plus AN times N dot T okay. Looking for questions out there. Don't see any questions. No hands. Okay. What's T dot T? A hint, it's the magnitude of T squared, which is what? Looking down, see if somebody types it.
Is it 1?
Yeah, it's 1. These are unit vectors, which I shouldn't have done a barb. I should have done a hat. So that's 1. And don't forget the relationship between N and T. What's their dot product? Oh, what's the dot product of N and T? I mean, I see that 0 in the chat.
It's 0.
Yeah, it's 0 because N, remember, is perpendicular. So we know that's a 0 dot product. So what you get out of that is that AT is A dot T. So I'm not yet finished with that. AT is A dot T. And now I'm going to remind you what A is. You know A is R double prime. T is R prime over the magnitude of R prime. That was the definition of the unit tangent. Oops. Magnitude of R prime. That's the definition. So normally when we write this formula down, we say that AT is R prime dot R double prime over the magnitude of R prime. Like that. And that's a computational formula. It's a little easier to compute using that. And so that's sort of recommended. And every, you know, it just depends on what you're trying to accomplish. You're going to have a string of formulas here. I'm thinking, make sure I didn't miss anything. Yeah, I think we got everything we need here. So let's do a quick summary, and then I'm going to try and squeeze an example in. It's just so many formulas. So A is acceleration. Which is equal to AT times T plus AN times N. And we've shown that AT can be computed so many ways. First, we showed that it is D2S over dt squared. That was the first one. Then just looking up, I see it's also R prime dot R double prime over the magnitude of R prime. Like that. Okay. Again, is that it? I'm trying to think now. Yeah, I think that'll do it. And if it helps, just remember this is the derivative. The first one there is derivative with respect to time of speed, which is the magnitude of R prime. So that's an easy way to get it. If you've got the speed, just take the derivative, and that's AT. Okay, and then AN. First formula I gave was that it was ds over dt squared divided by rho. That's the radius of curvature. But I also had that it's kappa times ds over dt squared. So those are really the same statement. But I also had that it's the magnitude of r prime cross r double prime over the magnitude of r prime. So these two are meant to remind you of each other. Okay, one has, they're both scalars. A couple things you can note that, first of all, the tangential component can be positive or negative, depending on the angle between your tangent vector and your acceleration vector. So this one's positive or negative. And you know that if the negative component, if the tangential component is negative, then you're going to slow down. But when you look at the normal component, this could be never negative. It just pulls you in one direction or another, but it's always a positive quantity. And then the vector itself points in a direction. Okay, I want to pause and see if there's any questions. Oh, okay, so there's a question that says down here. This is from Projectile Motion. He says, or she says, orthogonal, so 0, yes. Can you do the same thing for a sub n? Of course. We could also say a n is a dot n, and of course you'd prove that. But the thing is, we'll never use that. So I almost did. I decided, oh, why would I put that up there? Because I just don't see anybody using that formula. So I'm going to kind of tuck it over to the side here, because I don't want it to be treated seriously. I like doing a dot t here up above, because that turned into a formula here that looks a lot like the formula for an. So that's why I did that one. Okay. Any questions about any of this? How are we doing? 8:17. All right, let me see. I'm gonna look at my notes real quick and see if I could pull out a quick example. Oh, this one's gorgeous. You guys are just gonna love this thing. This thing, you're gonna want to take this thing home and just keep it nearby. Okay, so the example. And again, I come up with examples that I love because they have perfect squares and also inside of all of the square roots. So here comes r of t is a position vector. The components are square root of 2 times t. The t is not in the square root. And then e to the t and e to the negative t. Okay. I know I'm going to need some derivatives. So let's go ahead and do r prime of t. This is going to be square root of 2 e to the t and e to the negative, negative e to the negative t. Any questions? I don't see any in the chat. Nobody's just shouting out, so that means I'm going to keep going. Maybe we should do the magnitude of r prime. So I like to do that over here. So the magnitude of r prime is going to be a mess. So we're going to have the square root of 2 squared plus e to the t squared plus negative e to the negative t squared. And as you work this out, you're looking for a perfect square. So here, square root of 2 plus e to the 2t plus e to the negative 2t. Okay. E to the 2t is e to the t quantity squares. This is quadratic. So you can think of it as an e to the t squared plus a 2 plus an e to the negative t quantity squared. So again, you're supposed to look at that as a quadratic and factor it. And maybe you'll see it here, e to the t plus e to the negative t quantity squared. So you square the e to the t, you get the e to the 2t. Square e to the negative t, you get e to the negative 2t. When you multiply e to the t times e to the negative t, you get 1. Of course, you have to do that twice, so it becomes a 2. And we're set to go. So technically, you would do absolute values here. Absolute value of e to the t plus e to the negative t. But e to anything is always positive, so I'll make that note. This thing is positive. So then I will drop the absolute values and say that r prime is e to the t plus e to the negative t. Isn't that gorgeous? I told you you're going to love it. Questions? I'm looking for questions. I'm seeing nothing. All right, fine. Okay, then we got to do, I guess we have to do r double prime. Okay, so that looks pretty easy. 0 e to the t, e to the negative t. Okay. And then the question becomes, well, which formula do you want to use? If you're trying to compute AT, I almost feel like the dot product would be super easy. So, and you know, you can do this in 2 different ways. Oh gosh, yeah. Taking the derivative of speed is even easier, but let me show you real quick. You can do hang on, it's r prime dot r double prime over the magnitude of r prime. Okay, now I've thought this through, and I've already realized this is not the best way to do this. But I want to do it anyway. So if you do this dot product, you're multiplying component-wise, remember? And then adding, and the result is not going to be a vector. So careful with that. So you're getting, in the numerator, square root of 2 times 0, which is 0. I guess I can write 0. And then plus e to the t times e to the t. That's e to the 2t. And then this one's going to be a minus because you're doing a negative times a positive. So e minus e to the negative 2t. Okay. And then it's over e to the t plus e to the negative t. This, I don't know if you see it, but then this should be simplified because it can be simplified. And the numerator is the difference of 2 squares. See, the numerator is e to the t squared minus e to the negative t squared. So when you factor it, it's e to the t plus e to the negative t times e to the t minus e to the negative t. So that's just a difference of squares. And then over the denominator, e to the t plus e to the negative t. So kind of saw that coming. Hopefully you would see it coming. And as I said, this is substantially harder than the other way we're going to do, e to the t minus e to the negative t. Boom. Any questions? I'm looking for questions here. Nobody's talking.
I have a question.
Oh yeah.
If this was in the exam, and is that how you would just give it to us? R to the, of the t, you'll just give us the first information, and like, what do you want us to look for? Like, how would we know what you want?
You mean to simplify that thing?
Oh, is that what you want us to do? Simplify it? No, the initial. So when you wrote example,
Yes.
right? You wrote the components. Like, what is the question?
I'm answering a question that I didn't ask, right? So
yeah.
When I said, so when I wrote e to the t, or sorry, at down, that's sort of me asking the question. I'm doing examples of these formulas that we've done up above here.
Oh, just in general.
I'm just doing examples of these two formulas, AT and AN. And of course, you have a choice of which formula you want to use. And so
Okay.
what I'm really trying to do right now is to show you that the formula you decide to use matters. And sometimes it's going to be a lot easier than others. So let's do the other formula we talked about, AT, being the tangential form. I'll say also. AT, being the tangential component of acceleration, is the derivative of speed. It's the rate at which speed increases. So you can say this is d over dt, or d2s over dt squared maybe, or just d over dt of the magnitude of r prime of t. Okay, that's all saying the same thing. But magnitude of r prime is over there, so you can just say, oh, that's d over dt, e to the t plus e to the negative t. So that's e to the t minus e to the negative t. And of course, these match. And one was, well, I mean, they're both pretty easy, but the second obviously is substantially easier. But it won't always be like that. You just have to look at it and say, boy, which formula do I want to use? All right, any questions about that? All right, now for AN, I'm going to kind of slide back here and look at the formulas. I'd have to do rho to get AN. But you have to, I guess it's important to realize that these three formulas here are all really similar. They all come from the same place. So you're gonna pretty much do the same computations no matter which one of these you pick. Rho is computed with a cross product. At least there's an option for computing rho with a cross product that I showed you up above. But I think we should just probably just go with it and do this cross product here. So let's go with it. AN is going to be magnitude of r prime cross r double prime over magnitude of r prime. Okay, so we know the magnitude of r prime. We're going to have to do this darn cross product. So, and that's not going to be fun. So let me see here. R prime and R double prime. So I'm going to copy these down below. Maybe I'll start here. So R prime cross R double prime is going to be a cross product. Again, R prime had the root 2 e to the t e to the negative t. That's R prime. And then R double prime was just the derivative of that. Okay. Okay, and well, somehow I feel like I want this down on the next page. So here it is, and here we go. So with the I component, I'm multiplying diagonally like that and subtracting. So e to the t times e to the negative t, negative e to the negative t, I think that's going to be -1. And then minus the upward diagonal is e to the t times e to the negative t, which is again 1. Okay. Any questions about that? I don't see anything. Ooh, professor, R prime has a negative e to the negative t. Oh, thank you so much. You're the best. Who said that? That was projectile motion again. Where that is. So we're fixing a mistake here. Is that just going to change the sign of all this? So I see a 1 minus negative 1. Yeah, so it becomes 1 plus 1. Thank you. Okay, so mistake is fixed. Thanks, projectile motion. Continuing, minus j. And now for the j component, I'm going to go ahead and kind of shade out the middle part because we're going this way. Okay, so it looks like I'm going to have a root 2 e to the negative t minus 0. So just root 2 e to the negative t. Okay. I'm looking to see if anybody's making comments. I don't see any. Okay, and then plus k. And then I have to do a different cross multiplication. So here, I'm going to block this one out and multiply that way. So we're going to have a root 2 e to the t minus 0. So just a root 2 e to the t. Okay, so let me put this up real quick and see if you guys can agree. 2 negative root 2 e to the negative t and root 2 e to the t. Okay. Don't see any hands up and I don't see any comments. So I think this is probably okay. Now this is not great because we still have to take the magnitude of this. Remember, an takes the magnitude of r prime cross r double prime. I think we know this is really closely related to the last one we did. So I'm expecting the same sort of outcome, but let's see how it goes. So the magnitude of r prime cross r double prime. How are we doing for time? It's just 3 minutes. Let's go quick. So I'm going to take the square root, 2 square plus negative root 2 e to the negative t. That's going to be squared plus root 2 e to the t. That's going to be squared. So we get 4 plus 2 e to the negative 2t plus 2, yeah, e to the 2t, like that. Let's factor out a 2. So if we rewrite this way, with a 2 in front, then I'm going to rewrite this so that it looks like e to the 2t plus 2 plus e to the negative 2t. And then I hope you remember that that's a perfect square. So I'm going to bring the 2 out as a square root of 2. And then inside, I'm hoping we'll agree that it's e to the t plus e, that's not good. E to the t plus e to the negative t, and that's a quantity squared. Okay, I don't see any hands up. Looks like okay. And then just to be formal about it, root 2, I'll do the absolute value. The square root of a square is the absolute value, e to the t plus e to the negative t. And then once again, I'll note that that's positive on the inside. So I can drop that. Root 2 e to the t plus e to the negative t. Like that. And finally, we can finish by saying that AM, the formula is the magnitude of R prime cross R double prime over magnitude of R prime. And just to back up, we got root 2 e to the t plus e to the negative t over magnitude of R prime is way up here, and it was e to the t plus e to the negative t. Of course, that simplifies to just root 2. And why not, while we're here, let's do the curvature, because it's so closely related. So the curvature, as a reminder, is kappa. So if you're going to do one, you may as well do the other. Kappa is the magnitude of R prime cross R double prime over the magnitude of R prime to the third. So you can just do root 2 e to the t plus e to the negative t over e to the t plus e to the negative t, that's to the third. So obviously this is root 2 over e to the t plus e to the negative t squared. So that's the curvature. You just have to put the time in and you can measure how sharp the turn is. Okay, I don't think there's any way I can keep torturing you past this moment. I've already gone too long. I'm going to wait for a second. Actually, I'm going to stop the recording now.